Let's look at the graphs of some trigonometric functions, and let's start with sine x. We can see from the table here that when x goes from 0 to pi over 2, and those are the first quadrant angles, the sine values go from 0 up to 1. If we plot those values from the table on a graph, we get this. Now, in the second quadrant, you can see there's a symmetry. The second coordinate is the sine, so it's the same as it was in the first quadrant across this symmetry, and it goes down in value, the sine, as this angle goes from pi over 2 to pi. So when we plot that, we get a shape like this, and this is actually what that hump of the sine curve looks like. Now, how do we complete it? If you look in the fourth quadrant, you're going to see when the angle is theta and the sine is b, when the angle is minus theta, the sine is minus b, which means that the sine of minus x is minus the sine of x, and that gives us the same picture on this side but with negative. Okay, so this thing is reflected and reflected down, and that's one complete period of the sine curve, because once around, which is 2 pi, gets us back to where we started. And this is what the graph of the sine function looks like. It's periodic with period 2 pi, meaning that the sine of x plus 2 pi is exactly the same as the sine of x. Now let's look at the cosine function. Those are these values in the table, and you can see here that when x is 0, we start at 1, and in the first quadrant, we go from 1 down to 0. We plot those points, we get this. Now, if you look here, you can see the difference is cosine, which is the first coordinate. When we go from theta to minus theta, we have the same cosine, which means that the cosine of minus x is the same as the cosine of x, so this time this information is just reflected around, and we get this hump. Now, we could go through and get the rest of this using symmetries, but it's no surprise. It looks a lot like the sine function did, only it's shifted over. It's periodic with period 2 pi. Just a remark, you'll note here that the cosine of minus x is the cosine of x. Such a function, f of minus x equals f of x, is called an even function. And the sine had the property that the sine of minus x was minus the sine of x. That's called an odd function. So cosine is even and sine is odd. And of course, here's this other statement, which is the cosine of x plus 2 pi is the cosine of x, which says it's periodic. Once around, gets us back to where we were. Now let's look at one other trig function just to see how they plot. Y is the tangent of x, which is sine x over cosine x. So in the first quadrant, the sine gets bigger. The cosine, which is the denominator, gets smaller. And that means that sine over cosine is going to get bigger and bigger. And at pi over 2, the cosine is 0, which means you get an asymptote. Okay, now what about on this side? Well, the tangent of minus x is the sine of minus x over the cosine of minus x. And we know that the sine of minus x is minus the sine of x. And the cosine of minus x is the cosine of x. And that's minus sine x over cosine x, which is minus tangent, which means tangent is odd, which means you get this reflection across and then down. And that's what the picture looks like. And you've got an asymptote at minus pi over 2. And this picture repeats every pi. And the reason is, when we go from the first quadrant to the third quadrant, both a and b become negative, but minus a divided by minus b is a over b, so we get the same tangent as we got up here. So this thing is periodic, but with period pi. Now we are going to compute the derivatives of some of the trig functions. We're going to start with sine x, and there's one trig formula we did not talk about that is useful here, and it's the sum of angles formula. Sine of A plus B is sine A cosine B plus cosine A sine B. So we start by trying to find the derivative of sine x, and we use the definition, and it is the limit as h goes to 0 of sine of x plus h minus the sine of x over h. And this is where the sine of A plus B formula gets used. And we write the sine of x plus h is sine x cosine h plus cosine x sine h minus sine x. Now we're going to regroup this into two pieces. The sine x cosine h and the sine x end up in this term, and the remaining term, which is the cosine x sine h over h, ends up here. Now the reason we've done this is a sine x is going to factor out of this, a cosine x is going to factor out of that, and we're going to have this expression, sine x times the limit as h goes to 0 of cosine h minus 1 over h, plus cosine x times the limit as h goes to 0 of sine h over h. And if we can find these two limits, cosine h minus 1 over h and sine h over h, both as h goes to 0, we'll know what our answer is because we'll just plug them in. Okay, and it turns out that sine h over h is the key limit. So we start by drawing a picture, and the picture is of an angle in the first quadrant, h. The coordinates at this point on the unit circle are cosine h sine h, and there are some triangles. Okay, there's this small one here, there's this big one here, and you'll notice this sector of the circle is in between. So I'm going to draw that picture here. This area is less than or equal to that area is less than or equal to this area. Now this particular area is pretty easy to calculate. It's 1/2 base times height. So the height is sine h, the base is cosine h, so you get sine h cosine h over 2. This length is 1 because it's a radius of the unit circle, and this distance is y, which we don't know yet. However, we look at these two triangles, and they're similar triangles. So sine h over cosine h is the same as y over 1, and that tells us that y is sine h over cosine h, and the area is thus 1/2 sine h over cosine h. Now how about this? This is the sector of a circle. Okay, this circle is radius 1, and its area is pi r squared, or pi 1 squared, which is pi. So 2 pi radians get you a sector area of pi. Pi radians get you a sector area of pi over 2, and you can see what the pattern here is. The area of the sector is just going to be half of the angle. So the area of this sector is actually h over 2, and these three things give us areas. This area less than or equal to that area, less than or equal to that area. And we write that down as an inequality. This area less than or equal to that area, less than or equal to this area. Now we take this sequence of inequalities, we multiply through by 2, and we divide by sine, and we end up with the cosine of h is less than or equal to h over sine h, because we've multiplied by 2 and divided by sine h, and here sine h is gone 1 over cosine h. So cosine h less than or equal to h over sine h, less than or equal to 1 over cosine h. Now, notice that when h goes to 0, the limit of the cosine of h is the cosine of 0, which is 1, which is exactly the same as the limit of 1 over cosine of h, which is 1 over cosine of 0, which is 1. This expression right here is trapped between these two. They both go the same place. So according to the squeeze theorem, this limit is 1, which means its reciprocal has a limit of 1 as well. So the lim as h goes to 0 of sine h over h is 1. I've been doing this only in the first quadrant, but it works just as well if h is negative. Now what we want to do is find that other limit. And this was the other limit. Now the nice thing about this is we don't have to do any more geometry. We can do some manipulation. So we take this cosine h minus 1 over h and we multiply by cosine h plus 1 over cosine h plus 1. And on the top, we get cosine squared h minus 1. And on the bottom, we've got h times cosine h plus 1. Now what's the point? The point is that sine squared h plus cosine squared h is 1. Which means if you rearrange this by moving the 1 onto this side and the sine h onto the other, you get cosine squared h minus 1 is minus sine squared h, which is what we can substitute in there. And we get this expression, which we now break up into two pieces. We take one of the sine h's and put it here. We take this h, we put it there, and this is what's left. Okay, this limit is 1. And this limit we just plug in. 0, cosine 0 plus 1. So we end up with 0 over 2 times 1, or 0, which means this limit is 0. And when we plug into that expression we had before, sine x times this limit plus cosine x times this limit was the derivative of sine. We get sine x times 0 plus cosine x times 1, or cosine x. And that means that the derivative of sine x is cosine x. Now we can go through a very similar argument, and what we discover is the derivative of the cosine of x is minus the sine of x. Now let's calculate the derivatives of the other trigonometric functions. Keeping in mind we know the derivative of sine x is cosine x and the derivative of cosine x is minus sine x. The next function up on the list is the tangent of x, which is the sine of x over the cosine of x. So if we want to take the derivative of this, we're going to use the quotient rule, which says the bottom times the derivative of the top minus the top times the derivative of the bottom over the bottom squared. And we know the derivative of sine x is cosine x. And we know the derivative of cosine x is minus sine x. So we get here cosine x times cosine x, which is cosine squared x, minus sine x times minus sine x is plus sine squared x over cosine squared x. Cosine squared x plus sine squared x is 1. So we get 1 over cosine squared x, and 1 over cosine x is secant x. So 1 over cosine squared x is secant squared x. And now we add that to the table. And I'm not going to take the derivative of cotangent, but I'll tell you that it works the same way, and you get minus cosecant squared x. And now let's look at secant x, which is 1 over cosine x. We take that derivative again using the quotient rule. So we get the bottom times the derivative of the top, and the derivative of 1 is 0, minus the top times the derivative of the bottom, and the derivative of cosine x is minus sine x over cosine squared x. And that works out to be sine x minus sine x over cosine squared x, which we rewrite as 1 over cosine x times sine x over cosine x. That's secant x. This is tangent x. So the derivative of secant is secant x tangent x. And I'll tell you that the derivative of cosecant x is minus cosecant x cotangent x. Now that we have these functions, we can actually see that the product rule is worth a lot more than we had seen originally. So for instance, if you want to take the derivative of x squared sine x, there's no other way to do it than the product rule. The product rule tells us it's the derivative of x squared times sine x plus x squared times the derivative of sine x, and we know what those two things are. The derivative of x squared is 2x, and the derivative of sine x is cosine x. So the derivative of x squared sine x is 2x sine x plus x squared cosine x.